Well, welcome back. And as usual, let's first address the questions and issues from previous lectures and slides and labs. All right. So first, I've I've noticed that there are some questions about the detailed execution about MapReduce tasks, all right, in Hadoop. Um, so here I reviewed the slides and the video. It turns out that I maybe I can do a little bit better, so I will try this again from a different perspective. So trying to give you a better understanding of the MapReduce thing or the thing on these slides. So I won't repeat what I have discussed before, but let's take an example. Let's take analogy, right? So maybe we can see MapReduce. I mean, from a user of Hadoop, all right, and also Spark. Just from the user's view, we can see MapReduce, which is a programming framework, but we can see it as a black box. So it just you give it some instructions which are limited to be either map or reduce, and then it will give you a result. Or we do another analogy. Say MapReduce is like your manager who barely know any technical details, right? So you are a programmer. So the thing is, your manager always assign you the tasks, but he don't care how you implement it, as long as you implement it correctly. So he just tell you what he want, or more specifically, what the input is and what the expected output is, and then you do you write the program. Right? So in MapReduce, it's like so your manager can only assign two tasks to you. One is map and one is reduce, and it's here you is the map. You are the MapReduce, which is the programming framework, right? So your manager is actually you or the coder. So anyway, so for the MapReduce framework, it accepts the instructions or the orders of map and reduce, and it handles all the rest things. All right. So basically, using this MapReduce framework, you don't need to worry about how it actually works. You only give it a set of instructions formed by map and reduce, and it will handle the rest. So that's basically the idea or the advantage of MapReduce. So another thing is about Lab 1. So there are many questions in PIADA regarding Lab 1. So basically, I've seen that some of you struggled on installing this whole environment thing. So first of all, I have to say that the teaching team has put a lot of effort on this lab. We tried the whole procedure on different operating systems, but please understand that it is impossible for us to foresee all the possible errors and difficulties. So basically, it is it's possible. I mean, you've met some issues that are not specified in Lab 1. And also, I mean, the Lab 1 is when we do lab 1, we do assume that the operating system is clean. By saying clean is like it does not have a pre-installed Conda or notebook or Python. Other versions of Python, so on and so forth. But it's obviously will not be the case. So yeah, I'm happy to see that you raise these issues and questions, and I'm more happier to see that there are more people helping out in PIADA, right? So it is important to share your experience with your classmates, and also it is important to raise your questions when you met the problems. So we will collect your feedback and periodically, and we will give you instructions, but we cannot guarantee to give you the instructions in say in 1 day interval. It is possible it takes a couple of days, but the good thing is the lab 2 are expected to be released in I think probably in week 5. Yeah, in week 5. Yeah, and also the project will be released in week 5. So we still got enough time to sort all these things out. And it is important for all of you to make sure that you can run lab 1 correctly on your computer. Because under this special situation of COVID-19, we don't have face-to-face labs, and we don't have face-to-face consultations. So also, it could be harder for you to access CSE machines due to the network issues. So we do trying to develop the project such that you can do it on your own computer. Also, using different platforms, and also we can test your implementations on our side. So we're trying to develop a way to make that happen. So in order to do that, I personally, because I've seen some questions saying the Python 3.6.5 is not working. So you are trying, or you have already used other versions of Python, and maybe you are using other versions of PySpark as well. So the problem here is theoretically there won't be major differences. So I personally, I guess, with high probability, you will get the same result no matter you are using Python 3.6.5 or 3.7. But there's no guarantee, as I said. And as I've mentioned in this notes, I've mentioned here. So basically, we won't. After you have submit your project, your code for the project, we will not accept excuses such as it works fine on my computer. I don't know why it doesn't work on your side. So you shouldn't give me a 0 mark or something like that. Okay, because we cannot verify this under this COVID-19 situation. There's no face-to-face consultations. I can't watch you to execute your code on your side. We can only do it through internet, and personally, I don't trust I mean, if we do it remotely, it is not that convincing. I mean, yeah. So you just try to make sure that we are all on the same page, have the same environment. That is pretty important for the labs, rest of the labs and the projects in this course. And also, lab 1 is you do not need to submit anything for all the labs. All right, so there is no scores or marks for the labs. The labs is just to help you set the environment and to help you develop your skills. So it's you don't need to submit anything. All right. So let's come back, and last time we are stopped here with Spark architecture. Yeah, I also, I mean, it seems that we could explain the Spark architecture, I mean, in more detail, but after today's lecture, hopefully. So in order to do that, we need to go a little bit deeper. So the first thing here is to see how the data is transferred or shared in this whole Spark architecture. So that brings us the RDD, stands for Resilient Distributed. So basically, RDD is where the data stays in Spark, and it is the fundamental data structure of Apache Spark. So let's see let's introduce what is RDD just from its name. So first of all, RDD is a collection of elements, so that made it a data set. Right. So the elements here is equivalent to objects. So it can be integers. It can be a text. It can be a list of text. It can be a map. No, not map in MapReduce, but a map like a dictionary. So you have a key value pair and a lot of key value pairs. So these are all elements. All right. So the RDD is a collection of elements. So by distributed, we mean that RDD can be operated on in parallel. So basically, the data in an RDD can be split into chunks. Then these chunks will be logically partitioned across many servers. So you can do the computation or other operations on different nodes of the cluster. So back here, it's like, you have different worker nodes. So the RDD will be the data in RDD will be splitted and sent to different workers, so they can do their computation in parallel. So that is distributed. Resilient means that RDD is fault tolerant. So in order to have this fault tolerant property, it's thanks to the RDD lineage graph or the DAG. I mean, they are different things, but similar. Anyway, we will introduce these concepts later. So basically, we are able to recompute missing or damaged partitions if a node fails. So RDD is capable for rebuilding data on failure, which made it resilient. So that is resilient distributed data set. So as the fundamental data structure in Spark, RDD do have lots of features or advantages. So here we list 7 of them, which are like the most important ones, and I will briefly explain them one by one. Right. So first of all, in-memory computation. So basically, RDD stores the intermediate results in distributed memory, in memory on different machines, instead of store them on the hard driver. So it's quite different from MapReduce in Hadoop. All right. So for MapReduce in Hadoop, the intermediate results are usually stored on disk. Right. So this brings a large amount of cost on writing and reading these data. Right. We all know that the speed of writing or reading with memories are much faster, say 100 to 1000 times faster than reading and writing on hard drives. Okay, so that's in-memory computation. For partitioning, so partitioning is the fundamental unit of parallelism in Spark RDD, where each partition is a logic division of the data, and the user or the programmer can create a partition through some transformations on existing partitions. For transformations, we will introduce it later, and also, one can manually partition, which is important to make the partitions balance. So this will help the distributed data chunks more equally among different workers or executors. So this is partitioning. Fault tolerance, we have mentioned it before. So basically, thanks to the data lineage, we do have the capability to rebuild lost data automatically on when a node fails, right? And right, so a little bit more about the principle of fault tolerance. So the idea is because when we memory where the RDD is generated from, so you will say later like the RDD is either generated from an existing file or it is generated from another RDD with a transformation process. So as long as you know this and you remember this, you can recreate the lost state RDD. So that's basically the idea. Immutability means the RDD, the data on RDD is unable to be changed. So once it is created or generated, in this sense, the data is safe. Even we share across different processes. So it's kind of a way to reach consistency in computations. So any change on RDD is permanent. So the level of consistency is high. All right. So this is immutability. Next one is persistency. So the idea here is the users can state which RDDs they will reuse and choose a storage strategy for this specific RDD. For example, you either store it in memory or on disk. For example, the users can ask Spark to persist an RDD in memory so it can be reused more efficiently. Right? It does not need to write and read to and from the disks, right? Also, here by default, Spark keeps RDDs in memory, but it can. There are two situations that the RDD may be stored on disk. So one is that there's not enough memory. Then the Spark will spill the RDDs to disk. Another case is that users can request the persistence strategies, tell Spark that he wants to store the RDD only on disk, or the users can even ask Spark to replicate the RDD across different machines. So that's persistency. The next one is coarse-grained operations. So this is opposite from fine-grained operations, where coarse-grained operations means the operations, for example, the map or filter, and anyway, all these operations we'll see some of them later. But anyway, the operations will be applied to all the elements in the data sets. And fine-grained operations means the operation can apply to some or a part of the data sets. So in RDD, the write operation in RDD is coarse-grained. The read operation in RDD is either coarse-grained or fine-grained. The distributed shared memory, also known as DSM, is a very common memory data abstraction using fine-grained operations. So one major advantage of RDD over DSM is because of this coarse-grained operation thing. It is easier for RDD to guarantee the fault tolerance because all the operations are on the whole group of data. So as long as the RDD remembers, as I introduced before, like the lineage or the RDD lineage, or say all the previous RDDs and the operations of how they generated the current one, so it can recover the data more easily, right? But for DSM, because the operations are fine-grained, so the previous strategy is not quite feasible. Instead, DSM use checkpointing technique. So basically, the idea is to allow the application to roll back to a recent checkpoint. But every time you record a checkpoint, it costs time and space. So compare with the RDD lineage, which RDD lineage will actually acquire less space and less time. So that is the good thing about coarse grained operations. Location thickness. So RDDs are capable to define the placement preference to specific compute partitions. So this is basically where to allocate the RDDs or the RDD chunks. So later we will see the DAG scheduler, or for now you can think it as the cluster manager. Actually places the partitions in such a way that the task is close to data as much as possible, so it can reduce the time cost of transfer the data and speed up the computation. So yeah, these are the 7 major features of Spark RDD. And now let's look at how we create. So there are 2 ways to create RDDs. So the first way is to parallelize an existing collection in your driver program, or say when you write the code, it's like to parallelize existing collection. Here could mean a list or a text or a dictionary. Anyway, we will show the example later. And the second way is to referencing a dataset or load a dataset from an external storage system. So here the system could be HDFS, HBase, or any data source that offering a Hadoop input format. So then you can you can create your dataset on top of that. As we have mentioned before, the data in RDD will be partitioned, right? So for in the first case, normally the Spark, because the data is created from memory, so the Spark tries to set the number of partitions automatically based on your cluster. So usually how many cluster you have, then how many partitions it will generate it, right? And for the second case, let's say the data is read from HDFS. So by default, Spark will create 1 partition for each block of that file. And here, you can set the number of partitions manually, but for this case, the number of partitions can only be larger than the number of blocks, but it cannot be smaller than the number of blocks. Means that you can further partition a block, but you cannot merge blocks together. So that's the rules here. Now let me show you an example here. So by Spark, we need to import context and Spark configure. All right, so here, basically, you need to initialize a Spark context first. All right. And the Spark conf here is the configure of the Spark. You set the master to be local. Well, also in your project and in your labs, we all set the master to be local, means your local machine. And yeah, definitely you can use other parameters here, but because we are not able to try it on a real cluster, so let's set it with local here. The application name could be any name you like. It does not matter. All right, so I need to point out that you can only initialize one Spark context with one configuration file. So by doing this, you will see cannot run multiple Spark contexts at once. All right. So let's create a data first. Now you can create your RDD by parallelize the data, or you can view your data. View the RDD by calling the collect function. Or you see it's a set of a list of numbers here. We can also, as I've mentioned before, we can specify the number of partitions here, and then we can use GLOM to view data from different partitions. So as you can see, I mean, if we partition the data into 5 partitions, then basically each of them has 20 numbers here. All right. So this is the usage of parallelize. And also we have prepared a text file here. So we can also create another RDD say from the file on the disk. Now we can view the contents in this RDD as this. So basically it is a list of strings where each string corresponding to one line in the text file. All right, so these are how you create RDDs. And now let's look at the RDD operations. So similar to MapReduce, where the operations are map and reduce, in RDD, it kind of extends the operations to transformations and actions. So the typical transformation operation is map, while the typical action operation is reduce. All right. So basically, transformation is the function that takes an RDD as the input and produces one or more RDDs as the output. So the input and output are both RDD. And transformation can be further divided into 2 categories, which are narrow transformation and wide transformation. We will introduce them later. But remember, I mean, for all the transformation operations or transformation functions, they cannot and they will not change the input RDD, and they will output a new RDD. So when you do the coding, you probably need to store the results of a transformation into a new RDD. All right, that's the thing. And it worth mentioning that transformations follow the principle of lazy evaluations, which means that the execution will not start until an action is triggered. I know that we have mentioned this lazy evaluations several times ever since Monday's lecture. Today we will discuss it in detail, maybe a little bit later, to show you the advantage and to show you what is exactly lazy evaluation and the advantage of lazy evaluation. All right. So this is for transformation, and for action, RDD operations. Action is the RDD operations that produce non-RDD values, but it does take an RDD as the input. So you can think as the action returns of the final results, result of a set or a series of RDD computations. All right. And the value will be stored either to the drivers, or not a hard driver, hard drive. It's the driver program here, and or it will be stored to the external storage system. All right. All right. So narrow and wide transformations. So the difference between narrow and wide transformations. Again, remember that transformation is the operation that takes RDD as input and output RDDs. All right. So the narrow transformation involves no data shuffling, while the wide transformation involves data shuffling. Means, for example, the two individual data, if they are in the same partition before the transformation, they will still be in the same partition after the transformation. And if they are in different partitions before, they will in different partitions after. But for wide transformation, for two data in the same partition, it could goes to different partitions after the transformation. So there's no guarantee as in the narrow transformation. So when we look at the functions follow into two different categories, that we can see the typical functions or operations for narrow transformation includes map, flat map, filter, and sample. And for the operations or functions in wide belongs to wide transformation, they are sort by key or reduce by key, group by key, or join. Well, actually, join, you also need to look at the key. So this is not always correct, but it's usually, when key is involved, it's usually a wide transformation. This is kind of easy to understand. If the operation involves key, then you can expect that the organization of the data would be different due to different keys. All right. So this is for the narrow and wide transformations. And next is the action. So the actions are the operations which are applied on an RDD to instruct Apache Spark to apply computation and pass the result back to the driver, or to the store them in the external storage. So the action operations include collect, take, reduce for each sample. Sample should not be here. Can't save. Yeah, sample is not here. So action is like the end of a series transformations, right? So the name of transformation and action is kind of vivid here. So you can do a lot of transformation. You transform an RDD to another RDD, and you can further transfer it. But after all the transformations, finally you need to define an action over the RDD, and by the action you expect to grab a result, and usually the result is no longer RDD anymore. Well, this does not mean that the result has to be a number or a single string or whatever. but it's simply that the type is not RDD, and it kind of has something to do with the process of transformations and action, and also the RDD lineage and DAG, which we will discuss later. All right. So for the first half of today's lecture, that's it. We will show you a set of different operations in notebook, okay, to introduce their functionalities, and we will also introduce the concept of RDD lineage and DAG in Spark, so you will have a better understanding and hopefully appreciate the fault tolerant and lazy evaluations, such kind of topics in Spark. All right, so let's have a break.